series, what this is and what it's all about. So this class was started 3 years ago with kind of several main goals in mind. So when discussing and learning about environmental issues, it's quite easy to come at it from one or two different point of views, kind of based upon what sort of discipline that you are trained in. So with this class, what we wanted to do is show that environmental issues span the gamut of every single field that you can possibly think of, from psychology to journalism to earth sciences to engineering. So we wanted to have this class, we created this class so we could have researchers from Stanford come in from all these various disciplines and give us talks about the cutting edge research that is happening that relates to environmental issues. So being that grad students often do the leg of the research, we thought it'd be a good idea to invite the grad students in to give us talks about the research that they're doing. And we decided to host this in Robley Hall, given that this is the dorm that's kind of the leader in terms of sustainability efforts here on campus. So this is also a good opportunity for any undergrads that may be in the audience to learn a little bit more about what research is like, get exposed to grad students doing cool research, and hopefully derive some sort of inspiration from this. So today we have Katerina Gonzales from the Department of Earth Sciences, and she's going to talk to you about atmospheric rivers.
Thanks, everyone. Thank you to Hard Earth for inviting me to talk about my hard research, and thank you all for coming out on week 3 to learn about these rivers in the sky, whatever those are. So I hope by the end of my talk that we know how atmospheric rivers affect different sectors of our Earth system, and I'm really looking forward to our discussion afterwards after I present some of the questions I've been working on for my PhD. So, before we get into my dissertation research, I want to start with the motivation. And the theme for this quarter in Hard Earth is hot now. So climate change as it's unfolding right now and how it's impacting different areas of our Earth system. So this is where I start, is why am I studying warming climate? There are so many different reasons to study that. If I polled you and you probably have varied reasons. But my reason is kind of comes from a aesthetic reason, but also a curiosity point of view. So this is a picture of our atmosphere from space, and it's the thinnest layer of the Earth, the atmosphere, and it's the most dynamic layer. But before I was studying the atmosphere, I was studying hard Earth geophysics in my undergrad, so how rocks move and stuff. And spoiler alert, they move, but they move on a much longer time scale. And that's fine, but then I was like, well, I love weather, I love the atmosphere, I love how it impacts me on a day-to-day level. So I really wanted to apply my interest in that way. So it's really hard because it moves around so quickly. It's a very dynamic layer, but then you kind of add this other kicker to it. It's not just it's dynamic, and it always has been from the beginning of time. It's that we are pumping greenhouse gases into it, and stuff like our extreme precipitation and how that impacts our crops, that's changing right now as we speak. So that's interesting to me, and that's compelling. But honing in a little bit, I'm really interested right now in extreme precipitation. And even if you just think about the thermodynamics of climate change, if you have an atmosphere and you heat it up, then that atmosphere can hold more water vapor. Okay, so then in your baseline climate, yeah, you still get extreme events statistically, and perhaps that would cause some floods and some damage. But then if you heat up your atmosphere, add more water vapor to it, then extreme precipitation events become different, right? So we need to understand how our atmosphere is evolving and how that's impacting these tail end of the distribution events. So that's what I'm really motivated by. So now you're still probably wondering, what are these atmospheric rivers, or rivers in the sky? I'd never heard of them. Maybe you've heard of the Pineapple Express, but you think it's a movie. So we're going to go into, by the end, you can tell your friends when the next atmospheric river rolls around, hey, this is atmospheric river, this is what it looks like from space. So kind of technical definition, I'm sorry my GIFs don't work, but you can Google atmospheric river GIF and show it to your friends on your phone, it's beautiful. But so this is a picture of an atmospheric river, and in the colors is the amount of moisture in the atmosphere. So warmer colors, more moisture. So we have this elongated plume of moisture, and in this case it is extending from Hawaii to the California region. So actually this would be kind of a Pineapple Express type of atmospheric river. And the reason why these events are so impactful is just the sheer magnitude of moisture that these plumes are carrying. So you'll get a moisture intrusion in the tropics happen, and then the prevailing circulation, what it's going to do is it's going to carry it from the west to the east, and it's going to make landfall somewhere. And just to give you an idea of how much moisture that is, on average, atmospheric rivers transport more moisture than, like, if you would consider it a river, it'd be 7 times more water than the Mississippi. So that's a lot of water headed towards us, right? It's kind of a fire hose. Okay, so technical definition is just not the moisture though, it's the moisture plus these low-level strong winds, and that's going to have some implications for the impacts on land. Also, a little bit of atmospheric science is this concept called orographic enhancement, or enhancement by the mountains. So when you have this huge plume of moisture and it stretches from Hawaii, the reason why it rains out and dumps up so much precipitation once it hits land is due to this effect. So you have the winds carrying along the moisture. Once it hits a barrier like the mountains, that's going to force the air to rise and then condense, and then it basically dumps out a bunch of water. And this affects you, even if you didn't know it before. Here's a picture of our lovely campus just being drenched by rain. Sometimes we have to take the Marguerite instead of bike in, and that's a bummer because it's the Marguerite. And not only, again, is it the precipitation, but again, the wind. So I actually took this picture last week, the very own atmospheric river last week, and these bikes fell down because of the wind caused by the atmospheric river. I'm pretty sure someone didn't just kick them over. Sometimes people do that, no judging. But so it's both that combination of winds and moisture. And this has actually serious implications for the West and multiple facets of our human system, and can cause mudslides, which can lead to even fatalities, wind damage. This is a picture of the tree that fell down near the city, causing power outages. This was like last week, I think. And then flooding is a huge issue, especially in California. In the Central Valley, agriculture is a huge deal, right? So atmospheric rivers have the potential for a lot of hazards. However, there's a bad side, but there's also a really good side to atmospheric rivers that we need to appreciate and understand, is that even a few of these atmospheric river storms can lead to a drought being ended, for example, because they carry so much water. So we really rely on the snowpack in the West, and this is a huge motivator for the rest of my talk, is that without that snowpack, we wouldn't have that water resource in the summertime for our agriculture and sustaining life in these areas on the West Coast. Okay, so now I'm going to get into one of the questions for my dissertation. My dissertation broadly is looking at atmospheric rivers, why they are the way they are currently, and also how that is changing just in the observational era. So all the results I'm going to show you today are since 1980, so these are pretty recent changes, and they're ongoing. They're not from a projection from a climate model, for example. So we feel these effects already. So the question we're going to explore today together is simply, are there observed trends in atmospheric river temperature? Now, atmospheric rivers are changing already. Their moisture is changing. There are so many different aspects of their characteristics we could study. But for my first chapter, I just thought, okay, well, what if their temperature is already changing? That would have serious implications in and of itself, whether or not the amount of moisture stayed the same. So, we already know that in the past 5 minutes, we kind of have a sense that this is really important. So if we crank up the temperature, then the ratio of snow that falls from the atmospheric river in the Sierras, that's actually going to kind of turn more towards rain as we heat up the climate more and more. So when you have more rain than snow falling, well, one, you're not storing up the snowpack. Rain is it's more easy to run off a mountain than snow, right? So there are some hydrological implications, and then rain on snow is really bad because it creates this huge amount of like mud and runoff, and it's not good. So not only are there impacts for the winter time if this were to happen, but it extends into the summer, because like I said, we really need the snowpack, okay? So these are the implications of the question. And so here now to answer the question, the method. So I'm basically a sort of data scientist by training right now. And so everything I show you will be made with statistical analyses on data that are available by, say, like NASA and European NASA version and all these data centers, right? So my job is to come up with interesting questions about our climate system using available data that all my colleagues share. So to answer this question, first we needed to know where the atmospheric rivers were. And so this was actually probably the most complicated part of the research. And my colleagues at Colorado State, they kindly lent me their AR catalog. So they give me a list every single day. It says, AR president, no, 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 yes, yes, yes. So that was a huge step. So basically from those dates, then I'm using this publicly available data, which is actually assimilated from satellite observations and also station data on the ground. Lots of computational energy is going into these assimilated data. And then I take the temperature of the atmospheric river, and then I have a time series, and I could do my statistical analysis. All right, so now we're going to walk through what is going on already by region. And for this talk, I just want to note that trends, say, in British Columbia and Alaska are also important, but this is just the scope of the study right now. But atmospheric rivers do impact regions other than the US West Coast. So let's orient ourselves here. And these tiny dots, this is the atmospheric river temperature for each event that I showed you before from that AR catalog. So, and then by year, I have the yearly average atmospheric river temperature in the big dots. And so that's actually the time series that I'm conducting the average on, because some years can give more atmospheric rivers than others, so I didn't want that to be confounding. So this is for the state of Washington. Probably should have showed Northern California first, but you know, maybe some of you are from the Pacific Northwest, so feel validated. And so we have a statistically significant trend in atmospheric river temperature, and it's warmed in Washington about 1 degree on average. And so that is already important, but what is even more important is perhaps whether or not that's happened in more favorable months or not, but hold on a second, we'll answer that question. In Oregon, for this data set, we did not see a statistically significant trend, but we did see a positive trend. And then Northern California actually has the lowest magnitude trend from my analysis. We did the same thing for Central California, and then Southern California had the highest magnitude trend, nearly 1.5 degrees of change over this 37-year period. Okay? Okay, so now here are the trends by region and month. So in these bar graphs, what I'm showing you is that summary statistic, the change over time. So that's basically the slope multiplied by the amount of years. So in Washington, like I said, it's warmed like 1 degree in October. And then we have the cool season months because atmospheric rivers occur in the cool season mostly. All right, so what are we noticing here? Okay, so first of all, the trend magnitudes are different depending on the region. In Southern California, they seem to be higher than Northern California. And then also there are differences depending on which month of the cool season. So you'll notice that the red bars, which are these are the ones that are statistically significant at 95% level. These red bars, there are almost all red bars in March for all the regions except in Northern California. And November is also sticking out as a month in which statistically significant warming is occurring. Okay, well, why does this even matter? Like, all the months should be equal, right? No. So March is really standing out to me right now because from a water resources perspective, if you are warming the last bit of atmospheric rivers that you're getting before you head into the cool season, that's going to impact your water storage for the coming summer, right? So even if you had a really, really great winter and stored up a bunch of snow in February, what could happen with this late season warming is that it could bring rain on snow and it can melt the snowpack. So in some regions, especially in our region actually, late season snow is really important. However, it might depend on the region because atmospheric river frequency peaks at different times in different regions. So the news is different region by region, right? So, and in the Washington and Oregon, yeah, if you have rain, it's colder there than in the southern places. So rain in general is bad. So it's really about, and we're not getting into this now, but are you crossing that threshold at which you're not even snowing anything anymore? That's really kind of the question when it comes to impacts. But anyway, so March is heating up a lot, November is heating up a lot, and maybe the mechanisms are different, all right? So we'll get into that a little bit too. Okay, so I'm going to share with you something that is hot out of the RStudio console. I'm working on this paper right now, actually, and it's in revision for a journal. And one of the questions I got was, is this robust to the type of data set that you use? So before I was using the European data set, and then I decided to run it through 2 other ones. And then you'll notice that the colors changed. So just a moment of vulnerability with you all that this is, even for data sets about the past, there are some differences and different biases. So that gives you a sense of some of the difficulties of doing climate research. So we can talk more about that. But from now on, I'm going to focus on the results that I got with the European data set. But, you know, in a few months, my paper might come out, and then you'll be able to see the actual answer if you're like really concerned. Was it 2 degrees or 3 degrees? So stay tuned. So yeah, that's really important because in March in Northern California, that's like twice, almost, yeah, it's over twice the amount of warming. It's important. All right, so for the second part of this chapter, I was noticing these different trends occurring at different times of the year. And then I wanted to ask, well, what is really driving these trends? And it's not only just from an intellectual point of view, like we want to know why, but it's actually important because if we know why, then perhaps we can project more of that mechanism into the future. So let me walk you through this to give you a better sense of what I'm talking about. So here are a few different mechanisms that in this study we have as a framework. So I think the most simple explanation one might ask is like, okay, well we know that the continent has warmed up a lot in the past 37 years. Are you just capturing the trend of that background region, you might ask? And it turns out the answer is mostly no, because the ocean is warming, and it's warming at a different rate than over land. So, and as we know, atmospheric rivers originate over the ocean and are carried onto land. So perhaps there's this sort of blending of temperature from Genesis all the way to where it makes landfall. And then reviewer 3 was like, oh, what if it's the ocean? And I was like, oh yeah, it might be the ocean too, especially near landfall. So this is another mechanism we're exploring, because the ocean is really warming up here, then that would impact the atmospheric river right before it hits landfall. So we're going to walk through those, but all to say that it's a little complicated for atmospheric rivers. Okay, so to answer the track question, we had to go back into the algorithm, and my colleagues at Colorado State, who again are awesome, went ahead and backtracked every single atmospheric river and the entire data set, and they were able to show me the centroid of the air objects all the way from where it made landfall back to where it originated. So now, since we have where the atmospheric river traveled, some atmospheric rivers, as you can see, travel more north, some are more near Baja, so presumably these are going to have different temperatures before they make landfall. Okay, so then I used this data, took the temperature of each track, and then ran the trend analysis. And we'll get to that in a couple slides. And then briefly, for my giant intercomparison, so that was the AR track I just told you about. The background destination trends, those were easy to calculate, like I said. So if you remember, I had those different boxes drawn for each of the different regions. And for the background temperature, I just asked, okay, what are the trends in the monthly mean averages over the entire box? So that's just a sense of how much the climate in general has warmed with or without atmospheric rivers. And then this AR coastal, which is this upside down triangle, this is still taking the temperature of the atmospheric rivers, but it's before it hits land. So it's the atmospheric river over the ocean, and that's as a proxy for the SST influence. Okay. Yeah, just remember though, while we're comparing that these AR destination trends, those are the same ones I showed you earlier. Okay, so I don't know why I'm subconsciously showing favoritism for Washington State. I'm not even from there, but bear with me. So here we have different trend types, as indicated by the legend, as I just explained. And then based on those trends, those changes over time, again, as we did before, we can see which trend magnitudes were closest to each other. So for example, in March, atmospheric rivers warmed at about a rate of 2 degrees over that time period. Well, turns out that the AR coastal region also warmed about 2 degrees over that time period. But you know what else is interesting? The background temperature, the square, didn't even warm during that time period. So here in Washington in March, you have a situation where the background temperature in March on average is kind of staying the same, but the atmospheric rivers are getting warmer. So what gives, right? So if you were to run a climate model and say, I want to know if I can go skiing in Washington, and I'll just look at background temperature, then you might not be able to get that answer because atmospheric river temperature is different. All right, and then Southern California, the story is completely different. So here again, the trend magnitudes over time. We'll notice our favorite triangles, that's our AR temperature from before. So these were really high if you remember. But the trend that is closest, denoted by these things at the bottom, are mostly these squares. It's the background temperature. So in Southern California, as an example, you have really, really robust background warming in this area. And the atmospheric river temperature tends to go along with that. It's less than the background warming, but it's somewhere in between the tracks and the background. So let's kind of, again, imagine just that blending. That atmospheric river, maybe it's such and such degrees cool, hits a really warm background area and it warms up. And that's what may be driving the trend. Okay, so in the north, there was more upside down triangles, so this maybe suggests coastal SSTs. But in the south, we didn't see that much influence from coastal SSTs. All that to say, again, it's complicated, but it matters because we want to know what's going to happen for the future and in our ecological and our hydrological implications, right? Okay, so that was my first chapter, my dissertation, and so I want you to just remember as we walk away from here and as we move into our discussion that atmospheric rivers are high impact storms, both for the good and for the dangerous, and they're really important for our water in the West, which really compels me especially to study them more, but also compels us all as environmental scientists to study their impacts more. And we did find that atmospheric rivers are warming, right? So there were different trend magnitudes depending on the region and the month. But overall, they are warming, and this has implications for this higher rain to snow ratio, which again can lead to more wintertime flooding, more summertime droughts. And yeah, with that, I'm going to thank you and look forward to our discussion. Thanks. Yes?
Do we need a better sensor network around the globe for data, better data?
The answer is almost always going to be yes. And so this isn't my area of study in terms of the differences between the different observational products, but already from my results and my research, I can tell you that it is really important not only that we have satellites that are orbiting the globe, taking this awesome data, but also that we devote research funding to making really good simulations. So yes, we are getting better and better. And yeah, I won't say no to more data. Absolutely. Yes?
Two questions. First, when you said that the atmospheric rivers are warming, how does that impact, like, the temperature you might see on the weather forecast, like how we feel, the temperature we feel?
Yeah.
And the second question is, you said that there's like more rain over snow. What does that mean for the regions that don't get snow like here?
Right, okay, yes. So the first question was, how do we feel that temperature, even ambiently, as the atmospheric river storm crosses? So in the system of atmospheric river, this sector here will be the warmest, the atmospheric river sector, and then behind it, behind the cold front is going to be a really cold area. So actually, if you remember, like a couple weeks ago, it was really, really cold, right? I had to like crank up my heater. But then the past week, as it's been raining, those storms are actually warmer than it was a couple weeks ago. So yes, we can feel it. However, the biggest impact really is in the high country, and meteorologists, like snow meteorologists up in Tahoe and such, they really have a hard time nailing down the height of the atmosphere where it changes from freezing to above freezing. And so you can definitely tell that some storms, there are anecdotes that some storms are really, really warm. They come from like super tropical regions and they don't have a snow line. It's like way above the mountains. So it only brings rain. And people in the high country, then they're concerned for flooding and such. So I guess that's the main place where it would impact, for sure. And then your second question, what was your second question?
I said that you mentioned that there's like more rain to snow.
Oh, yes.
What does that mean for like places that don't even get snow like here?
Yes. So rain on snow. So for Southern California, I think that's a good example of the place that doesn't get a lot of snow. So Central and Northern California, that's where the Sierras are, and that's where you really have to be concerned about this. Southern California, it's not necessarily a concern about rain on snow, because it would just be rain anyway. But then rain anyway has, again, that higher potential just for really quick runoff.
Wouldn't that be good for like when Southern California was in like a drought?
It could be good depending on how much and depending on the soil condition. So runoff depends on like how hard the soil is, for example, or if you recently had wildfires. So if you recently had wildfires and you don't have vegetation, then a lot of runoff actually is very bad and leads to those mudslides that I showed you. So that becomes more of like a ecological question at the moment. It's like, how is my soil doing? Can I afford for it to rain a lot? Will I be able to soak it up? Sometimes the answer is no, and that leads to really costly effects. Yeah. Yes.
I apologize if you already covered this in the lecture.
Oh, no worries.
But the databases that you're looking at, the NASA, European, why were you getting different results? Was it because of the assumptions they were making, or?
Yeah, so I don't have a straight answer for that question, because all of these products are assimilating thousands and thousands of observations, and you would think that they're using all the data they can get. However, when people build their numerical models, they're usually they usually start off to build it as a weather forecast model, and then using that and the equations that go into that, then they kind of rerun it over the entire, like 1980 to 2016. So there will be some biases in like which effects one model will pick up rather than the other. However, the European one and the NASA one, when I looked at moisture transport, they were pretty similar. And so it was just the temperature differences. But then when I compared like the NCAR one and the NASA one, the NCAR one had much lower moisture transport. So I'm dealing with that now. And one issue too is resolution. But I think it comes down to like which models are catering more towards like the effects they really wanted to capture. But I was amazed in a bad way. But yes, I don't really know. Mm-hmm. Yes.
So you kind of mentioned that, you know, an output of this kind of research would be including this in climate models. So I guess, do any climate models take into account atmospheric rivers and having any sort of different temperature? Or is this like very new? And then going to what you were kind of hinting at before is how much work has been done on like total moisture content in these rivers changing over the past few decades, if at all?
Mm-hmm. Yeah, so I'll answer the second question first. Is there has been a study that's found a trend in moisture content due to just the moisture. I meant moisture transport. So the winds have been generally staying the same, but the moisture has been increasing slightly. However, I don't know how many different products they used, right? So now I'm skeptical. But people are really interested in that question because that has to do with the, I guess, extremeness of your water falling. So people are more actually focused on that question in the field right now. And in the future are running the climate model saying, oh, how much is moisture transport increasing? Like, yeah, so they're running that now. But to tie into your first question, there isn't necessarily, I don't see there being a complete synthesis for like an atmospheric river targeted climate model per se. However, I will say that resolution is really important and climate models are even more coarse than the data that I'm using, just because computationally they're running more experiments. So if you read a paper about atmospheric rivers in the future, like they say, oh yeah, it increases and we found these blobs, but we don't really capture the sort of thermodynamics of the atmospheric river feature that well. We are, And this field is new, about a couple decades old, but it's at that course resolution. But to end this question on a more like action-focused note, so I don't think necessarily the question is, oh, what are the climate modelers, are they listening to this research? That could be one thing, but I think another thing is for the research community to listen to this research, but also the sort of the hydrologists to listen to this and implement that into their water forecasting, the policymakers to, plan for dams that will hold more rain rather than the snowpack up there. So there are things that we can do as scientists in our little realm, our separate realms of science, whether it's, if you're studying fish that live in streams or if you're studying water. So we all don't have to be climate modelers per se, which is good because I'm not even a climate modeler, right? Oh, yeah, go ahead.
Right. I'm so sorry if this sounds a little ignorant. I'm not studying any climate science or any PhD science. I'm just kind of here, but
Awesome. This is what this is for.
yeah. So, okay, let's say if I was, oh God, this is gonna sound a little bit silly, but if I was to take a walk outside
Mhm.
and it was raining, would I be able to tell the difference, like if this is like an atmospheric river or it's just casually raining?
Yeah, no, that's a great question. I get that a lot too, because
Okay.
people want to know when it's raining. Oh, is this the atmospheric river? So the short answer is no, not really. It actually, different types of systems impact our west coast, and some of them are just normal extratropical cyclones that don't have atmospheric river in them. And so you get precipitation, but it's not sourced from the long filamentary plume. And you wouldn't really be able to tell that walking around because if you look up, the whole sky and your periphery is going to be covered by clouds. However, if you were a satellite, you can be able to tell. And that's how you would be able to say, okay, this is extending this far, and like based on these like aspect ratio criterion, now I can say, oh yeah, this is an atmospheric river, it's being sourced from here. But that's a really good question, actually, and it's a question that the community has wrestled with in a more technical way up until about a couple years ago. So when I started my PhD, people didn't even agree on what an atmospheric river was. And so when I was starting my PhD, I was like, okay, like, how do I detect atmospheric rivers in my data, much less, see it on the Weather Channel? And people didn't really agree. Luckily, the community kind of came together, they held town halls, and they're like, okay, this is the atmospheric river, we're gonna put it in the glossary. And then people started building these algorithms to detect it. And there are so many different algorithms that now they are intercomparing all the algorithms to see which one does the best job of capturing different features. So it's still, like the flavor and the spirit of the question is actually very, very relevant. Yeah.
So then is the reason that we're hearing more about atmospheric rivers recently because the definition has just been recently agreed upon, or is it because the frequency is increasing, or?
Yeah, it's kind of a communications phenomena, I want to say. Not just that we agreed on the definition. We've had the word atmospheric river since, I want to say 1998. But if you were to look at, or if I were to show you a graph, one of those boring graphs of papers using atmospheric river over time, it's really has risen exponentially in the past 15 years. So it's a combination of people being able to communicate with the public, especially on the West Coast, that this is an atmospheric river. Once we communicate that well, then say the news people catch on to that, and vice versa. And so once you hear about it on the weather, on Twitter, then you're like, oh, like this isn't just a made-up term. So yeah, it's kind of been a kind of synthesis of that. So a good communication story, hopefully. Yeah. Yeah.
From that picture, that atmospheric river, the red thing, right?
Mm-hmm.
That thing's over land, right?
Yes. Right now, it's making landfall. It's like brushing up against the Pacific line.
Is there any difference in how the atmospheric river like behaves once it gets to the ocean? Or does it not go to the ocean?
So is there a question?
Like, does it change in any way when it goes over the ocean versus if it's on like land? Or maybe if it changes from a different region, like a drier place to a more humid place, and the river.
Yeah. So there are a couple different changes that I'm thinking about that align with your question. One is, if the atmospheric river is passing over a region that's, say, warmer SSTs or just higher moisture, or plants can provide moisture to the air, right? So that could impact it. I think the first order impact of like ocean versus land atmospheric rivers is going to be that orographic enhancement thing I talked about when it hits the mountains and the mountains make it go up. That's going to be the biggest impact that something on land has on an atmospheric river. But I also will say that it also depends on the orientation of the atmospheric river. So this one is kind of up and down, and as I said, it's kind of like brushing up against the Pacific Northwest. But if we were to draw wind vectors, it'd probably be like the dominant wind vector would be up here. And what people have found is that when atmospheric rivers are sort of like oriented perpendicular to the mountains, that actually causes the most efficient rainfall because, you're hitting your barrier right on than just kind of like skating by it. But that's sort of the opposite way around. It's like that the topography is not changing the atmospheric river per se in that one. It's more of how does that affect our impacts. But yeah, I think as far as pre-landfall enhancements or stuff, like we're kind of just barely getting to these questions in the community. People are studying aerosols, for example, and how that impacts precipitation of atmospheric rivers. Because if you put a bunch of dust in your atmospheric river, the hypothesis is that the vapor has more particles to cling onto, and maybe it makes it rain out more. I'm not an atmospheric chemist though, but people are asking these questions for sure. Was there another question in the back? I don't remember. Okay. Yes.
Apart from the western U.S., what other regions get hit by atmospheric rivers?
Yeah, it tends to be the west coast of continents. So the UK gets atmospheric rivers, Norway especially, just imagine those steep mountains really enhancing the atmospheric river once it hits it. So those are the huge areas. The Iberian Peninsula also, because atmospheric rivers can sometimes travel that way. And like Chile are like equally impacted as we are. It's just there's a study bias for the West Coast right now. And then there are some kind of random and fun areas that get atmospheric rivers that you might not think of, like Antarctica gets like a subset type of atmospheric rivers, which, if you're in Antarctica, you're really cold, and if you get an atmospheric river, it's like comparatively much, much warmer. So then you get like ice melt, and so there are even sort of cryospheric people studying atmospheric rivers. The same thing happens with Alaska. Not a lot of people have been focused on Alaska atmospheric rivers, but almost always when an atmospheric river comes to Alaska, it's making stuff melt a lot, and floods are a huge issue there. So yeah, anyone can study atmospheric rivers. There's plenty of world for us to study atmospheric rivers, but yeah. Yes?
So if it is kind of this thing that tends to be, like you're mentioning, on the western coasts,
Yeah.
has it been the case that like different regions are talking about atmosphere and atmospheric rivers like appropriately and responding, or is it kind of just the conversation is a bit more general and being applied to everything?
I would say that the regions that I mentioned, like the UK and Iberian Peninsula, there's a whole community of European scientists who are they're atmospheric river scientists, and it was cool. I went to this conference last summer, and we brought together people from all over the globe, and they had their perspectives, and we had our perspectives, and they're both atmospheric rivers, and they talk about it, and they're equally impactful, but actually it was interesting, and I won't be able to go into all the details that I don't even know, but atmospheric rivers behave differently depending on the hemisphere. And so research like this, or research that looks at the moisture in an atmospheric river, or even the algorithms that are being written, they have differences depending on what hemisphere you're looking at. But so I think, for example, for like Chile, the scientists are starting to talk about this more and more, but they're a little bit, like the public isn't quite aware that these are atmospheric rivers as, you know, say a random passerby in California. So it's all forward progress for sure, but I think especially for Chile, we would need more data down there, like some radars to see if the atmospheric river is coming and stuff. So yeah, it's truly something global.
Well, I think we're just about at 5:20, so if anybody has any last questions, feel free, but otherwise that's...
Oh, one last question, yeah.
In Al Gore's movie, he talks about rain bombs. That's the end of a atmospheric river. Is that the same thing, or it comes in?
Not necessarily, no. Yeah, I have not. Yeah, I wouldn't be able to point at the. I don't know. I was gonna
It's
say.
basically dumping a bunch of water.
Right. So they're different mechanisms. Yeah. So, yeah, I won't. I can't recall in the literature where bombs are associated with atmospheric rivers. There might be, but it's not really.
That's a different thing. Then.
Yeah, it's a different mechanism. Yeah.
Okay.
Yeah.
Thank you.
Yeah. Cool. All right.
Cool. Well, let's give it another round of applause.
Nailed it. Hello. Sorry, I was so late. It's okay. I was just sleeping. Need a crazy.